questions about internet security. We want to be able to secure our data sent across a public network, across the internet. We've got different ways to do it. We've gone through several times the different layers: application, transport layer security, network level. With regard to network level security, and we're using the example of using IPsec. So that's one protocol that allows us to take our IP packets and encrypt them before we send them across the internet. Everything's sent across the internet. In our perspective, we're using the internet protocol, IP version 4. But IPsec adds this extra feature to allow us to encrypt those packets. As a result, someone who intercepts those packets cannot see the original content. So that's our aim, to keep the data confidential. But we saw there are different variations of IPsec. In this case, in this example, if someone in the internet, so between router X and router Y, so even though it's shown as just a single link here, it's in fact, and maybe multiple different networks, if someone malicious there intercepts the packets, so on one of the devices or one of the links in between these two, they intercept, what do they see? Do they see the data sent between A and B? Then what do they see if they don't see the data?
They see a
header and ciphertext. So because it's encrypted, the data which host A generated, it was encrypted by IPsec here. So we can think the data is the plain text when we return to encryption, and therefore the ciphertext, the encrypted data, is included in the packet. And we still have an IP header included in this packet. We cannot encrypt the IP header because to send data across the internet protocol relies on reading especially the destination IP address in the IP header. So when host A sends an IP packet and eventually arrives at router X, why did it arrive at router X? Because the destination IP address in that header says B, and using the routing tables it knows to send to X. And then X has this IP packet. You can think it has the header, which has source IP, A, destination IP, B, and other fields, and it has the data. And the data is encrypted here, the ciphertext. And X uses the destination to be B and realizes, okay, I need to send it to another router, and it goes across the internet until it arrives eventually at B. So be aware that if you think of the IP packet, the data is encrypted, but the header is not. Because we need the header to be in the clear so the routers can forward the packet across the network. If we encrypted the header, then the routers would not be able to send it on, because they wouldn't know who to send it to. The routers use the header to know who to send to. So if someone intercepts in the internet, they see the ciphertext, they don't see the data, but they do see the header. We had another case using IPsec. Another variation where we used it from the host to a router, and then this last portion of the path, this last segment, we don't use any encryption. The benefit being that host B doesn't need to know about the encryption. Host B doesn't need to support IPsec. The router does it on its behalf, making the setting up of this host simpler. This router can use IPsec for many hosts inside the internal LAN. And then a last one, we use IPsec between two routers. Okay, so different options: router to router, router to host, host to host. And we can have combinations of different levels. We've used IPsec as an example. I think one slide here. There are other protocols that do similar functionality, and the two that you'll often come across are called PPTP and L2TP. point-to-point tunneling protocol and layer 2 tunneling protocol, but they are used in a similar manner to IPsec, so there's not just one. And these are used to create a VPN, a virtual private network. Anyone have a mobile phone? Open it up and see if you can find the VPN features. If you have a mobile phone, see if you can find something about network settings and see if you can find anything referring to VPN. And tell me what it says. I don't know where it is. It's usually under network settings, some maybe advanced setting. Should be something about VPN. VPN, okay. And when you select VPN, what does it say? Some warning. Okay, keep going. See if you can set up a VPN. So on the iPhone, just go back. On VPN settings in the iPhone, you see you can add a VPN configuration, and you see 3 different types of VPNs: L2TP, PPTP, and IPsec. So on the iPhone, it will be different than Android. And on Android, then again, you can select different types of VPNs. So it depends upon the operating system. So on Android, you see PPTP, L2TP, and IPsec, different variations of IPsec. Okay, so what you can do with your mobile phone is set it up like this scenario, where your mobile phone is host A, think that's the VPN client, and let's say there's some router on the internet, say the SIT router, which runs a VPN server, and if it's configured correctly, what you do on your mobile phone is you set it up so that you enter into I think you'd enter in the address and some maybe username and password for the VPN server. SIT has a VPN server. And what would happen then is when you use your mobile phone to access the internet, those applications that use the VPN would send their data using IPsec or one of those other protocols encrypted to the VPN server. Okay? And then on from there to wherever the destination is. So you can set it up on hosts, a mobile phone as an example. And that's a difference between, one of the differences between network level security and, let's say, transport level security. To use the network level security, the VPN, you need to set it up on the host. And in fact, there needs to be a server running to allow you to use it. Okay, so you need to do something. When you use, let's just go back, when you use HTTPS, which is specifically HTTP over TLS or SSL, do you need to set anything up? No, you just open your browser and you type in HTTPS and then some domain. Okay? And then it does the encryption for you. So with HTTPS or transport layer security in general, the user in practice doesn't have to do anything, which is much more convenient from the user's perspective. So with transport level security, the security is built into the operating system and it's performed automatically if you use HTTPS in this case. So the user doesn't need to configure anything. Whereas with network level security, the user usually needs to configure something on their host, and in fact usually there's a server set up to support the other endpoint. So that's why, in fact, network level security is not as common as transport level security. That's one of the reasons. So if you use network level security, you need to set up usually the endpoints. The user needs to do it, which takes some effort, and not everyone can do that. Yeah?
If someone in the internet,
Someone's in the internet and intercepts.
in the gateway, in the internet gateway and can see the
Are you referring to this one?
yeah.
Yep.
Can they see the packet routine and analysis?
Okay. We'll get to that in a moment, but let's see, what can someone in between host A and host B see? What can they see? Well, they can see, as we said, we can see the ciphertext, it's encrypted, and we can see the IP header. And that's it with the data transfer. We'll see what that gives us, but that's all they can see. The packet is encrypted, so with the data transfer, all they see is, they see the packet, they don't see the contents of the data, they do see the header.
How about the time and the packet?
If they see the packet, yeah, I think you're getting at, can they do some analysis?
Yeah.
Yes, they can see the time when the packet got here, because they know when it arrived if they capture. So they can do some analysis about when the packet was sent and received, how big the packet is. But many encryption schemes use fixed size packets anyway. So maybe you cannot determine anything about what's happening. So the main point here is that they cannot see the data, but they can still see that there are packets being sent. Let's continue on that point. Let's look at with the tunneling mode of IPsec, what happens is that there's the original IP packet and it's put inside another IP packet. So the original one going from A to B and the data, so this is the IP header, this is the data, is actually put inside another IP packet which is being sent from A to Y in this example. And the internal packet is encrypted. If you intercept on the internet, in this case, what do you see? If you intercept, someone's on the internet and they can intercept the packet being sent, in this example, what do they see? Yeah, this gives the hint. They see, this is what they see, this is the packet. This red part is encrypted. So from the attacker's perspective, they don't see anything here but random bits. They cannot determine anything about the contents. But they still see this header. What do they learn when they capture this and intercept? What does an attacker learn if they can intercept here on the internet? Anything? We know they can't see the contents of the message. What do they learn? The time, okay, let's say there were thousands of packets, so they can see things about when the packet was sent. Okay, because if they can capture, okay, I receive it at 11:55 p.m., then we know something about when the packet was sent. The size of the packet, although often there's some compression done there. What else do they learn? Where it's from, who it's to. Again, the IP header is not encrypted. And the IP header includes many fields, but two important ones are the source IP address and the destination IP address. So in this example, when you intercept on the internet, what do you learn specifically? The time, size,
And how many packets?
number of packets, and source and destination, which are in this case A and Y. Okay, someone who intercepts on the internet sees that this packet was sent from computer A going to computer Y. All right. So now we're starting to move into the area of not so much about can the attacker see the contents of the message, but could they do some further analysis and learn something useful to the attacker, some traffic analysis to work out who is communicating, how often they're communicating, what types of patterns of communications with respect to time, at what time of the day are they communicating. So even if we encrypt the data, the attacker can still see the outer header. and at least can learn who sent and who received. But look at the differences. In this case, if we intercept on the internet, we'd see that the source is A, the destination is B. We'd learn that A and B are communicating. In this case, the attacker, if they intercept in the internet, would learn that A and Y are communicating. So they don't really know that A is originally sending the data to B. They just know they're sending to this router Y. So whether it's host B, C, D, E, or other hosts that it was destined to, the attacker only knows it was going to router Y. So we've hidden some detail from the attacker in that case. We hide the fact of the specific destination. And in this case, if the attacker intercepts in the internet, who do they know or who do they think are communicating? X and Y. If we intercept this packet, we see the source address is X, the destination is Y, so the attacker, all they learn is that this data is for communications between X and Y. So they cannot learn the specific hosts which are communicating. Let's say this represents SIT, our campus, this is the Rangsit campus. Then the attacker knows that someone on either of the campuses, or both of the campuses, are communicating, but they don't know specifically who. When I say who, they can't identify the specific source IP address and destination IP address. They can only identify the routers which are communicating. So we're moving into this issue of privacy. What can someone determine based upon intercepting packets in the network, even when we use encryption? And in IPsec and similar, in this case, someone can determine the routers which are communicating. So let's look at that a little bit more and look at how people can track what others are doing in terms of communications and how some of those things can be hidden. Let's come back to, yeah, question?
How about if we combine host to router and router to router?
Host to router, this one.
And between the router Y and host B, we have another router.
Okay, another router here, yep. So we could use another encryption form of encryption if we had here.
Yes.
In this case, we're looking at, let's say this is the public internet,
Yes.
okay, where someone intercepts. So it depends on where they intercept as to what they can do. So if there was another IPsec from this router Y to some router Z, well, if the attacker was on this portion of the network, they would intercept between X and Y, but if they were on this portion, they'd intercept between Y and Z. So they'd learn the source and destination based upon where they intercept at. The same can be applied across multiple segments.
Can the malicious user like outsmart the security? Like,
Can the, yeah, how?
Like the reality is that the host A and host B are communicating, and the
Yep.
security is just A to router Y.
Okay. So what can the malicious user do? In this case, we're assuming, let's for now assume the malicious user is in the public internet. For example, this portion of the network may be internal to an organisation. So the malicious user can't get physical access to intercept here. That may be common. And therefore, let's say that they can only intercept on the internet portion in our diagrams. So in that case, they cannot see any data sent across here, that's encrypted. All they can see is the source and destination address of those packets. And in this specific case, A and Y. How do they outsmart or how do they defeat that? Any ideas? What else could they do? let's look. And let's now address the issue, well, what could a malicious user learn about people communicating? Even if they cannot see the contents of the data, can they determine who is communicating? So this is the issue of privacy. Not necessarily privacy of the data, but privacy of what you're doing. Trying to prevent others from determining who's communicating.
So my very detailed question is, in the internet, every point we use the IPsec to connect each other. So if the malicious user attack or intercept, they only know the only some router, only a shortcut part, only a host to host.
Yes, if we extended this and used encryption across between one router and another router, and then different encryption across another, then yes, we can start to hide some of the original source and destination a little bit better. And we'll see a way that that's done. But note that there's a big problem with setting that up, in that every router needs to be set up at each endpoint to use IPsec. The benefit of, or the problem of setting up security is that we need to do something on these computers before this works. If we need to do it on every computer in the internet, it's just not practical. But if we can set IPsec up on one router inside SIT, and maybe require the users who want secure connections to set it up on their phones, maybe that's practical. So we'll see, we'll hopefully get to a case where we can start to hide the communications. Let's look at what the interceptor can learn. So let's focus on privacy. When, let's say host A is a web browser, host B is some web server, if there was no encryption here, does the web server know who contacted it? Does the web server, what does the web server know about who requested the web page? And how does they know anything? So I'll just go back to one of our first pictures, just ignore encryption. This scenario, host A is you on your browser, host B is some website you're visiting. And let's look at privacy and think, okay, what does the web server know about you? What do they know? IP address, okay? Because we're sending an IP datagram, it's sent across here. Remember the IP datagram, the header contains the source IP and the destination IP. So that's received by the web server. So for sure, the web server knows who sent the datagram. It knows your IP address. What else? Does it know your name? Well, not necessarily. Maybe. It knows your IP address for sure. We cannot avoid that. Port numbers, okay, not very useful because the source port just identifies some application. If it knows your IP address, what can it learn about you? What can the server learn about you? Do they know, can they find your name? Country? Yeah, if we look at IP addresses, the way that IP addresses are given out, that is, how did your host get an IP address? They're actually distributed by internet service providers. Let's say this is your home computer. The IP address that your home computer, or more precisely your home router gets, is an IP address in the range managed by your ISP. And that range that your ISP has is publicly known because there's a register that maps ISPs to the address ranges that they have. And in most ISPs, we can then work out, well, which city they are in and which country they're in. So IP addresses, it's usually not too hard to map an IP address back to a rough location. a city, a region, a country at least. So, host B, the server knows the IP address of the source. They know where they come from, roughly. Anything else? Okay, so they can learn that about you. So if you want to keep that private, using just the normal internet communications is not possible. That is, the server can learn about your IP, and from your IP learn your location, your ISP even, which company you're going via. Can this web server learn your name? How? How does it learn your name? Like your real identity, not your IP address as the identity. Well, two basic ways. If you log in, if this is Facebook, of course, if you log in, they now know who you are. Okay? That is, if you log in as some user, then that web server could associate this login with this IP address. And maybe the future time someone contacts that server from that IP, they could assume it's the same person. Okay? So if there's some past behavior that has given out the name, then maybe the web server can determine that. But how else is that done? What's the technology we use for logins? You eat them. Cookies, okay? Remember a cookie, when we log in, for example, there's a cookie stored on your browser, and that may be stored permanently on your browser. The next time you visit that website, your browser sends the cookie to that website. Even if you don't log in, it may send the cookie. So the cookies are used for the website to get more precise tracking of who you are and what activities you're doing. Because if you've logged in once and you return to the same website even without logging in, the cookie is still sent to that website, and the web server can identify who you are or map it back to the previous communications. So the cookies are used by the servers to track more precisely who is contacting this server, not just based on IP address, but based upon usernames in some cases and other things. Now the server can learn how often you contact it, because every time you send the cookie, it knows that it can keep a log of how you've contacted it. And even if you change your IP address here at the host, but your browser sends the same cookie, the server can now keep track that it's you again. Okay? So even if you have a different IP address, the cookie allows the server to keep track of who's contacting it. So IP addresses can be used to track who is communicating with a server. And IP addresses can tell us roughly the location of the client. In terms of web browsing, cookies can be used to track who is accessing a web server. And they usually give more precise information because they can be used, because sometimes IP addresses change, whereas cookies remain the same. How do you not get tracked? Well, yeah, but how if you use some private mode in your web browser, what does that do? Okay, don't use cookies. That'd be one way. You can set up your web browser not to use cookies. But I think you find many websites rely on cookies to provide that feature of personalizing the website. So if you don't use cookies, you never send them, you can still access the website and it'll be harder for them to track you, but you may not get the features of the website that it normally offers. Okay? So there's a trade-off there of the convenience and the privacy. If you want to use cookies, is there anything else? Does encryption help? not really. Okay, so you're just encrypting with HTTPS. Again, with HTTPS, the IP address is still included. The cookies are still included, so you gain nothing in terms of privacy in that case. That is privacy from the perspective of the server identifying who you are. If you use encryption, someone in the internet cannot track your communications, but the server still can. What other issues? I think you've all seen similar websites which tell you your IP address. If I open my browser and access some website, there are websites that will tell you the IP address of the client. That is, I'm accessing from my browser to some server. The server tells me what is my IP address. There's some website that will look that up, and it tells me my IP address, my client IP address is 203.131.209.66. The ISP is Thammasat, and it tells me my location on a nice map. So approximately it tells me accurately to the city level. Okay, so this is what the server knows about my client, about me. Similar, if someone intercepted the packets on the internet being sent between my browser and the server, they could determine this, because it's just based upon IP address. So if someone here intercepted the packet I was sending that server, they would see my IP address and they would know my location. And similar for the server, they'd see their IP address and be able to identify their location. If they could get cookies and other information, they can maybe even get more precise details. Does this IP address identify my laptop? Anyone else have a phone or a laptop? You want to visit this website? What do you get? What is myIPaddress.com? Let's see what people get. What'd you get? Same or different? It's the same. Your IP is the same as mine. What do you get? The same. Okay. Well, that's not right. You know in the internet that computers have different IP addresses, but in practice things are a bit more complicated. Inside most organisations, we use what's called NAT, Network Address Translation. And what happens, you think this is the IP address for SIT. Okay. My computer has one IP address, 10.10.6. something. Your computer has a different internal IP address. But when we all access the internet, we all send packets to the SIT gateway, which performs this feature of changing our internal IP address to this public IP address, 203 address. And then the SIT gateway sends the packet to the real website. So when the real website, whatismyipaddress.com, receives the packet, the source is this 203 address from everyone here. And when they send back a response, the SIT gateway, this network address translation, does this thing of converting back to the original IP address, so my computer receives it. So you may have studied NAT in another course, but it's common in organisations to have, say, one or several public IP addresses, like this one. Everyone internally, from the outside world, are represented by this one public IP address. That's why you see everyone with the same address if you're inside SIT. So maybe we've improved privacy a little bit here. The web server or someone who intercepts this packet will find this IP address. They'll recognise, okay, this is someone at SIT, but they can't identify whether it's me or someone else inside SIT. They cannot find that out. So we've hidden to some extent, the internal user, and in the public internet, people can identify just the network or the organization that's communicating to the server. Questions?
Yes. For the location, as my experience, when I connecting from anywhere in the country, but the location is still in the ISP of it.
Correct. The information that's known by the server is just the IP address. But there are mappings that I said that internet service providers have a range of IP addresses, so therefore they work backwards. Given this IP address, what range is it in? It's in Thammasat's range. So now they know the ISP. And then you can have databases that say, okay, where is Thammasat University located roughly? Well, here's the city, region and country. So it's more, it doesn't give a precise GPS related location, it gives a location of where that ISP is registered normally. So maybe there's an ISP, maybe you're on the Thammasat University network, but you're in maybe, or if you're in another campus or some other location accessing via this network, you may not be in Bangkok, but it will show you as in Bangkok. So the location is really just some address of the ISP, some mailing address of the ISP.
And another question about the private IP. The website, do the website get the private IP too? Because some website like pandit.com, they will show the public IP and they will show the private IP too.
No, they do not. Okay, so in this case, in the normal setup, my computer address that I've got from SIT, what is it? My wireless LAN 10.10.11.10, that's my computer IP address. That is only used internally inside SIT. Okay? That's my actual computer IP address. Your phone will have a different one, 10.10 something. But when we send a packet outside of SIT, the SIT router changes it to this one public address. Therefore, anyone outside of SIT will never see that internal address, unless something's set up wrong or some other special feature is enabled. But in the normal case, no, they'll only see this as the source address, and therefore only identify that. So, can now someone at the server or someone who intercepts, so again, the server sees this public IP address, 203, someone on the internet could intercept and see that 203 address. Can they still map it back to me? Ignoring cookies, how could they find out that it was me, Steve, accessing that website and not someone else? What's needed in that case? Let's say a law enforcement organisation is trying to trace who accessed a website, who sent a particular message or posted a message on a forum. They know where it come from, this public IP address. That's easy to obtain, either intercept the packets or the logs from the web server. How do they work back to find who's the particular person that sent that message? What's needed for that to be possible?
They have to see the log from the organization.
They would need to know. So let's say they know this address. They would need to go to Thammasat, specifically to SIT, and say, at this point in time, someone used this public IP address, and that mapped to a local internal address, some 10.10 address. Which computer had that local 10.10 address at that point in time? So they'll need to go to the organisation that owns this public address, and if they have logs, let's say of the past 1 month, which internal IP addresses map to this address, then they could work back and find the internal IP address. Okay, so it depends upon the organisation that has this public address, say SIT, if they have some log, some record of who used this at what times, which internal IP addresses, then another organisation could trace it back to the original person. Okay. Does SIT have logs?
Yes.
In some countries, it's a legal requirement to have such logs. And yes, SIT would have logs of specific IP addresses, your MAC address of your device, maybe even your login for your SIT login, so they know who actually sent to this via this public IP address. So in most cases, they do have logs. That's how people can trace originally back to the original sender, even if they're inside an internal network. But that requires some non-automatic means, some legal means, or some personal contact to get that information. It's not something you can do across the with a protocol. How do you hide from that? If there are such logs, so that even if we know the public IP address, we can eventually get the internal one, is there a way that users can still remain private? That is, visit a website without someone in the internet intercepting and finding out that you visited that website. What are some technical ways you could do that? A proxy, okay? A proxy. Let's try. So here's my IP address. I visited the website. It identifies me. Let's refresh. Let's hope it works. I'm now in Japan. Okay. My IP address identified from this website that I accessed is now this 106 address, and it locates me at this different ISP in Japan. Why? Well, what I did is I set up a proxy so that my browser, instead of sending direct to the website, my browser sent to some intermediate server, a proxy server, and that proxy server then sent onto the website. The website identifies the proxy server, which is some server in Japan. Okay, so that's one way to hide the communications. How do you do that, or what did I do in Firefox? There are two steps. In the advanced settings in your browser, usually you can go up to the network settings, and you can set up proxies. Okay. And I'm not going to go through the details of how that works, but I set up a proxy to use some port 9998. And then the second part, well, I need an account on a proxy server. Okay. You cannot just connect to any proxy. So I have an account on a proxy server, and I set up the connection from my computer to some proxy server, and the result is when I visit a website, my browser sends that request sends it to the proxy server. The proxy server forwards the request onto the real web server. When the response comes back, the real web server sends it to the proxy, which then sends it back to my browser. We can draw that. So, just quickly, what happened, we had my browser. we had a proxy server and the web server, the one I wanted to contact. And what happened is that my browser was configured to first send the request to the proxy, not to the real web server. So it sends the request to here that get some web page. The proxy then creates that request, then takes that and sends it to the real web server. But the source IP address here is my browser computer, and the destination is the proxy. And then the proxy sends the same request, get some web page, but the source address will be that of the proxy. And of course the response will come back. And I'll draw that in a moment. So 3 computers involved now. My browser trying to access a website, but it was set up to, it said, forward the request from my browser to a proxy. And that IP packet that was sent across the internet, the source address would be that of my browser, the destination that of the proxy server. If someone intercepted this between my browser and the proxy server, they would see the source address and destination matching these computers. So they'd be able to identify that my browser is talking to a proxy. My proxy is set up to then send that onto the real web server, because in fact this packet includes the address of the real web server. I will not show the details, but it includes more information here. The proxy sends the request to the real web server. The real web server thinks that the request came from the proxy. That's the source address. And keeps a log saying, okay, the computer with this address just contacted me, and sends back a reply to the proxy. Maybe 200 OK. The real web server doesn't know I used a proxy. It just sees the IP address of the proxy without knowing any more details. Then the proxy forwards that final reply back to my browser. As a result, the web server doesn't know it was me that contacted it. It knows, or it thinks it was this proxy. It knows the IP address of the proxy server. And someone who intercepts between the proxy and the real web server, again, they don't know it was me that contacted it. Because when they intercept, all they see is the source and destination address, and that identifies the proxy and the web server, not me. Okay. So this is one way to hide the source. Hide it from the server, and also hide it from people who intercept here. Any questions about the proxy in this case?
So in this technique, it can get some special content that provide in specific country, like a content from PBS is provide for in the US only. So can we use this technique to access that content?
Okay, so Yes, as you saw, the web server identified in my example the proxy in Japan. Some websites provide content based upon where the source comes from, where the client comes from, some location-based serving of content. So, in fact, if I visited Google via that proxy, I think Google or the search engine would show the search page in Japanese because it thinks I'm in Japan. If I visit from a proxy in Germany, then maybe it shows the website in German. Okay, so in that case, yes, the server doesn't know anything about where the original source is. It thinks the source is where the proxy is, and therefore would serve content based on where the proxy is, especially if it's a location-based content. So if it's content like streaming videos, which are only accessible if you're in a particular country, then the same thing works. What's the problem? Slow. Okay, we have a performance issue here. Instead of going direct across the best path in the internet, we're sending to one server, which then sends to some other one. So in this case, if I was accessing a website in Thailand, what happened? My browser sends to a proxy in Japan, the proxy sends to a server in Thailand, and then it sends back to Japan and then back to Thailand where my browser is. So that's very suboptimal in terms of performance. What's another problem? Can someone trace? Can the server find out who you are, specifically your IP address? Or how can they? What do they need to do? They know who contacted them, that is, they know the address of the proxy. Can they find out the original source? The same way that someone could find out, based upon the public SIT address, who the original source was, if the proxy keeps a log of who sent this request. Okay? So if the proxy has a log of what happened in the past, and if the server could then request that log or get access to that log, then they could find out who accessed it. So you're placing your trust in the proxy operator. They now know, the proxy operator now knows the websites you visit, and if the proxy operator has a log, then it's still potential, there's a potential that the server operator can find out who the original source was. But maybe it's better than not using a proxy in that case. But now we shift the trust or the point of failure to the proxy. And of course you need a proxy which has some cost and some performance degradation. So we're just going through different issues with respect to privacy in internet communications. How to hide who is communicating, not just the content, but the people or the entities communicating. Why hide? Why do we need to hide? Why hide? Any good reasons? Protect.
Hide from attackers.
To hide from attackers?
To attack a real target.
Okay, so if you want to hide from malicious users who are trying to find out who is communicating with a particular server, yeah, maybe. Yeah. Okay, maybe we will not discuss it, but you can think of different ways. Why would you want to not let a server know you're contacting that server? Okay, and there are many valid and as well as maybe invalid reasons for people to do that. Okay? Why do you want to keep your communications private? I think you can think about different ways, different reasons for that. Maybe you're in some organization or in some country which is not allowing you to access some servers, but you think there's a valid reason for doing so. Therefore, hiding the fact that you're doing it may be a way to get around it. So, yeah?
Can I go back to the proxy? I saw in many websites that provide a free proxy.
Mm-hmm.
And you said that the proxy have a cost, right? And what benefit to
No.
use the
Let's say, okay, let's say my intention at the browser is so that the server cannot identify me as visiting their website. That's my intention. So by going via proxy, the server cannot identify me, but the proxy can identify me. Okay, the proxy knows I visited that website because I sent a request for that website to the proxy. So you must place some trust in the proxy not to release that information. Okay? So running a proxy has some cost involved. Okay? It's an actual computer or multiple computers. So if there's a free proxy, then what do they get out of it? Maybe some people are doing it for free for the good of mankind, but in other cases maybe they're providing some advertising, or maybe they're collecting your data. So they're collecting information about what you're visiting to maybe sell that as advertising and other purposes. Okay. So if the free proxy is or any proxy is compromised, if an attacker gets access to this proxy, then the attacker now knows which websites you're visiting and can release that. So yes, you place your trust in the proxy now.
So the attacker can provide a proxy.
Okay, so if someone wanted to intercept and providing, here, I have a free proxy, connect via me, and now that proxy knows, if everyone uses it, knows where everyone else is, where they're visiting. So maybe that's an attack in its own right. Can we improve? Yes? How? Use multiple proxies, maybe? Send via one, which gets it to send via another, which sends via another. Making it harder for the final server to trace it back to the original source. Okay? But performance is much worse now because we're sending via all these proxies. Use encryption. Now, although we haven't mentioned here that this communications can be encrypted. Proxy can offer encrypted communications so that the request from browser to proxy at least is encrypted. And that's what happened when I did my demo. And in fact, the next step up is in fact to consider like using multiple proxies, multiple intermediate nodes to send via, so instead of a single proxy, plus using encryption, and plus using encryption in a way such that one proxy can only determine about the next proxy but not the subsequent one. In this case, the proxy knows the server. So the proxy learns the server you're contacting. A better approach, and we'll not go through it, but the idea, a better approach would be, I have a picture somewhere. To finish off for today, a better approach would be, say, your A, the destination is F, to essentially go through multiple intermediate nodes So you want to send, let's say F is a web server, you want to send a request to it. You don't want F to know who you are. And similarly, you don't want the intermediate servers to know that you're communicating with F. Okay? If you have a single proxy, it will know who you're communicating with. And we won't have time to go through the details, but just the concept. Then the concept is to, let's see if we can draw it. What A does to send to F, it negotiates secret keys for encryption with each of these intermediate nodes. And I'll denote them as what? K, let's call this one KB, KC, KD, and KE. And A has those keys as well. We'll ignore the details of that step, but let's assume that they have some secrets shared between them. Let's get this correct. So let's say they have secrets so that A and B know KB. So if we encrypt something with KB at A, only B can decrypt it. C cannot, D cannot, because they don't have KB. So we have these secrets shared between these nodes. A wants to communicate with F. What A does, it creates a special packet. How do we draw it? It creates a packet with some data. We need some space. I'll draw it here. The data that it wants to send to F and I'll draw the entire packet and then explain. This is we created it, the source A. This is the data. And inside these header parts, these special headers contain the destination. Destination F. This would be destination E, D, C, and B. And it encrypts portions of that. So this part is encrypted with KE. This part is encrypted with KD. And we keep going, fit it in, KC, and the last part. This is the packet created at A. It wants to send this data only to F, but we want it to be private, and private in two manners, so that F doesn't know that it was A that contacted it, and that the intermediate nodes don't know that A is communicating with F. Okay, that's our aim. And this is the concept that A initially exchanges secrets with each of these intermediate nodes. Then A creates this packet containing the data, and we can think of this as an IP header where the source address doesn't matter, the destination is F. In this second one, the destination is E, D, C, and B. This part is encrypted with KE. That plus the header saying destination is E is encrypted with KD, and this part KC, and all of this with KB. This packet is created at source A. Sends to B. Okay, the first step now. We send this packet to B. Let's see, if someone intercepts at this point, who do they know is communicating? So if someone intercepts the packet here, the source is A, it's coming from A, it's going to B. If they intercept, they know A is sending a packet to B. Okay, they know the destination address, the source address would be A in this case. So they know A and B are communicating, but the contents of that packet, so here's the header, the contents, this part on, is encrypted. So someone who intercepts cannot learn the contents. B receives this. What does B do? B decrypts. B knows KB. So B removes the header, decrypts the internal part because they know KB, therefore they can decrypt it, and they get all of this. Now look at all of this. What is it? It's this part, C, and the rest is encrypted using KC. Does B know KC? No. KC is shared between A and C, not B. So from B's perspective, it knows this packet needs to go to C, but it doesn't know the contents. B knows so far, I've received a message from A, I need to send it on to computer C. So it sends on to C. If someone intercepts there, they would see just a message going from B to C. They don't know it came from A. Okay. So B sends on to C. C receives this part. It's the destination. It was encrypted with KC. C decrypts. It removes the header. And now we have destination D and the internal part encrypted with KD. What does C know? Who sent it? From C's perspective, B sent the packet. From C's perspective, the destination is D. Does C know anything about A?
Yes.
What do they know about A? Do they know A sent this packet?
No, but they have to do a handshake for a key first.
Okay, you're right. The key is known to be shared with A. In fact, so you've gone a step ahead of me. The keys, we'll see, can be also exchanged in a secure manner that we're using for the data exchange, a private manner. Forgetting about the keys, what else does C know about A? In terms of the IP source and destination address, C received a packet from B, source is B, destination is D, so C knows that B and D are communicating. Forgetting about the keys for a moment. C sends it on to D, you can see what happens, the same. D removes the header, decrypts, realizes it needs to send on to E. E removes the header, decrypts with KE, realizes to send on to F, sends to F. F receives the data and has the original data. Ignoring the keys for a moment, if you just look at who sent it, who received it, each node is only aware of the immediate source and the next destination. C is only aware that the packet came from B and went to D. C doesn't know that it's actually going on to E then F. Because all of that, from C's perspective, E and F, the values are encrypted with keys it doesn't have. When E receives the packet, it doesn't know that that packet came via A, B and C. Because all it sees when E receives the packet, this part, It sees E is the destination. It knows it came from D because D just sent it. And it knows it needs to send to F when it decrypts, but it doesn't know that before D there was C. And similar, you can see that each node only knows about the one that sent it to it from the previous link and the one it's sending to on the next link. As a result, F receives from E. It doesn't know if it came via D, C, B or A. So the end result, and we'll come back to the keys in a moment, is that the destination doesn't know the original source, and the intermediate nodes do not know the original source or the final destination. All they know is on either side of them. The way that we do this encryption, they cannot learn about who else was in the path. And that provides the true privacy of communicating to a server without the server knowing who you are and without people intercepting and finding out who you're communicating with. If someone intercepts here, all they know is that C and D are communicating. They don't know A and F are communicating. It's encrypted. But come back to the keys. We said at the start, A needed to exchange keys with D, for example. Yes, but in fact the key exchange uses the same approach. We do it one step at a time such that D, when it receives a key, it doesn't know it's from A. It has a key, but it just knows that it's for this type of packets. It doesn't know who is the original source. So the packet is created, this packet is created at a source. It has multiple layers. What's it called, the packet? Any names? What has multiple layers? And as you send that packet to B, B takes off this and sends the inside to C. C takes off this layer, sends the inside to D. And eventually F receives the data. We start with a packet with multiple layers, and as we forward it along, we peel off the layers. What do you peel layers off of? What food do you peel layers off? An onion. Okay, this is referred to as an onion. Okay, see, he likes onions. So that's the concept of, people talk, this is an onion, and as you forward it through, you peel off layers until the contents, the original data, gets to the destination. And the name of this concept is called onion routing. That's where the name comes from, onion routing. We're routing packets, and the concept is that we have this layered packet, which is referred to as an onion. And the abbreviation is called TOR. TOR onion routing, or the onion router. So this is an anonymous routing or an anonymous communications protocol that's used on top of the internet to provide that true privacy of servers not identifying the source and intermediate nodes not identifying the source and destination of communicating. TOR is one example.
Is it 100% work?
In the concept that we've discussed, yes. But of course, in any security scheme, there's always practical issues to consider. So there are always limitations, either due to implementations. This assumed all of these nodes, A through to F, were using this protocol, this TOR protocol. And in this case, the server cannot identify the source. But in practice, if you want to access a normal website that doesn't use the TOR protocol, then you have some extensions to handle access to normal websites. So TOR provides anonymous routing or anonymous communications amongst special sets of computers in the internet. These onion routers, these devices. we're not going to go into any details of that. That's just an initial starter. No questions in the exam on TOR. Okay? There's no questions on that. Any questions on some of the issues we've raised about privacy? So privacy from the perspective of not letting others find out who is communicating. Not just the data, but the entities communicating. We've seen several issues. What you should know for the exam about privacy is maybe just the initial things that we started off. We have a picture. For example, if someone intercepts, so if there's an exam question, if someone intercepts here, what do they know about the entities communicating? What privacy or what level of privacy is provided by this IPsec configuration or another configuration? And in terms of privacy, think about who can we identify as communicating? We can always see an IP address, a source and destination, but which computers are they identifying? In this case, in this example, if we intercept on the internet, we'd see it's A sending to Y. So we'd be able to identify A and Y communicating. What else have we gone through? TOR will not be in the exam, just that general concept of privacy. The proxy, so we had this example of a proxy. Proxy related to privacy is not in the exam, but if you go back to firewalls, you'll see there are some slides about proxies in the firewall topic. They're used as a firewall as well. So that may be in the exam. But proxies related to firewalls, not related to privacy. Okay. Finish for today. Questions? Yep.
On our privacy, how we can protect from the government agency?
In theory, this provides some protection. Okay. In theory, if you have enough, not just with 6, but if you have many of these special onion routers, then you can start to communicate in a public internet anonymously. Of course, things like, let's say some attacker runs these anonymous routers, runs many of them, then it becomes hard to protect against. But assuming they're not owned by the attacker, then you can start to protect. Okay, Thursday, what will we do? Thursday, we'll just mention the exam. So this afternoon, I'll put some hints on the website about the exam. I will not start any new topics on Thursday. Anything that we need to go through on Thursday? So read the hints on the website today. Maybe look, what's the time? If not by 1 p.m, then look maybe after 4 p.m. today. You'll find the hints on the website. I have a lecture. I need to put them on there. And then Thursday, I'll just be here to answer any questions or provide any comments about the topics that we've covered in preparation for the exam. The exam is when? Monday. Okay? Less than a week.